Professor Kuri is originally an engineer from Nahuatl University. He has a master's in computing science from the University of Illinois. He also has a PhD in computing science by the Kennedy Western University. He has written at least 9 textbooks, at least 110 articles published in journals, and also dictated international conferences. He has twice received the UNAM's medal for university merit. He has directed at least 30 theses of master's and doctorate students. He is, of course, member of the national system of researchers. Among other types of recognition to his work, he received an award for the best research paper during the 7th International Conference on Data Mining in Leipzig, Germany. He has chaired the Mexican Society of Artificial Intelligence. He also belongs to the assessment committee of CONACYT. In computing, he has also been an entrepreneur, therefore he does know about applications. He was founding partner of 2 companies, Micromex and IDET. He was also director of applied research at the SIC, the Center for Research on Computing, by the Polytechnic Institute of Mexico. He's member of the board of Iberemia and also member of the Mexican Academy of IT. He's also a member of different associations in his field, and he is emeritus professor at the ITAM, the Autonomous Technology Institute of Mexico. He's also a member of the doctoral committee at the postgraduate course of computing science at the University of Mexico, and he's also an external consultant for Bancomer Bank. So it is for me a pleasure to introduce Professor Ángel Kuri. First of all, I would like to begin by organizing Infotech for organizing this meeting, as well as to Dr. Villaseñor for having invited me, and to Dr. Gomez Larrañaga for all his hospitality during these couple of days. I would like to begin by apologizing because I will be speaking in Spanish, so if you need simultaneous interpreting, please request your headsets. And my second apology is because my presentation does not have a lot of equations. It only has one, and I will let you know in due time so that you can applaud. But in reality, after having attended yesterday's morning session, I could not stay because I had other activities, and I noticed that we had a very heterogeneous audience. I know most of you are topologists and high-level mathematicians, so I apologize because I will try not to use a lot of math and that sort of thing during my presentation. Now I will discuss something that we call computational intelligence for to mine integrally reduced data sets. That is difficult to understand. So I would like to begin by defining what I mean. If somebody could help me change the slides. Well, I do not know who I'm talking to. How can I change the slides? Now, where should I point to? And what if I want to go back? Well, it doesn't matter with the tech support of the young men here. I am sure I'll be able to do this. But well, I would like to begin with the agenda of my talk. First, big data is a term, a phenomenon. Yesterday, during the talks, it was said that big data is here to stay, and I agree. However, this induces a technological dilemma I would like to discuss, and about a likely conceptual solution to this induced dilemma that has to do with the management of information and the concept that we have borrowed from thermodynamics, but that is used a lot in computing science, which is entropy. We'll discuss also modeling and how can we apply this to the technical side, and finally we'll discuss an application, because I try to make sure that what I do can be used somewhere. Sometimes I cannot achieve that, but I try. And now we have already said a lot about what big data is. I just want to emphasize that this is highly distributed data that is apparently unstructured and that is of a very large volume. This is what being part of the big data phenomenon means. Well, I'm sure I'll manage to work this out. Well, big data was born from actually arises in many areas, from social science, from exact science, many others. I'm just mentioning some of them. I will not repeat them. You can take a glance at the slide. The important thing is that the source of data, well, the origin of data comes from many sources that are at first disconnected. And in reality, what is important from my standpoint is that the big data phenomenon arises because computing systems have become increasingly inexpensive. And it is not only that they have become inexpensive, they have also become more efficient. And this produces a very interesting snowball effect. Not so many years ago, around 30 years ago, the cost of using a computer with the features of the laptops we have now was 100 times more costly. But there were no computers like that. The computers that did what now a laptop can do would occupy a room this big. I at times once worked at the computing center of the Ministry of Finance. There was a room bigger than this, much bigger than this. They had an enormous computer and tape devices, and they were really boastful about their 2 GB storage capacity. The cost has decreased, and computing equipment is increasingly faster and more efficient. There's a lot more they can do, and I am sure that some of the topics that will continue to be addressed would have been possible to years ago. And it is not only because there is an increased data proliferation. The growth of this data proliferation has been exponential because it costs less. Now we have better tools to store, to transmit, and to analyze data. And that makes it possible for us to have further information, and that gives us more data. And what we need to do now is to find technological solutions that can enable us to somehow manipulate that universe of information. And now I'm going to discuss these subjects very lightly because these have already been addressed and will continue to be addressed. And these are not new concepts. These are concepts that have just become somewhat fashionable because and these couple of examples we have right here are systems. Their technical names are not very important. These are names of the people that invented them. But the main purpose of them is to transfer information from one set of processors to another. When you're working with thousands of processors, as it happens now, it is very important to find a way, well, to have information going from one to the other. It is not worthwhile to have information processed in one of the processors if it is not going to be sent back to the rest. And that is the feature that underlies our work with large data sets. We divide the information in segments in order to divide the complexity of the calculations needed on different segments. Computing systems, the computing systems that underlie these figures do not appear. Each one of these lines expresses that there's a different computer on the other side. Another question is, how can we transmit information from a 1,000 computer network to another 1,000 computer network? And this is how Baynes and Batcher networks were created for this purpose. And I will not delve into this, but I just want to say that this is now giving rise to new technological challenges that did not exist in the past. And on the other hand, what has prevailed lately, given the large amount of information that is now available, is the need to work with parallel computing, the optimization of grouping algorithms. The issue of topological analysis has to do with that, with the way in which grouping algorithms are optimized. The fact that we are now working with distributed computing and grid computing, well, these are the technologies that are more fashionable as of now. And also, new paradigms are being explored for the same reason. And very briefly, one of the new paradigms is that instead of working with computers that operate with electricity, this is not very new, but is now very much in vogue. There are computers that are working with lights, light rays, sorry, not electricity, not electric currents, and that is because heat dissipation, heat generation is much lower because photons dissipate less heat than electrons, and it happens when working with high-capacity computers. You have seen that there are a lot of computers that work with the tiny fans to prevent them from burning up. But when working with light rays, that is minimized. Another very interesting type of technology is cryogenic technology. Years ago, a Dutch citizen found out that if something is cooled a lot, then it loses all electrical resistance. That means that it does not heat anymore, but also that means that if you inject an electrical current, that electrical current will remain there as long as the device is not heated. And this phenomenon is called the superconductor phenomenon. Probably many of you have heard about the famous Higgs boson. It was developed in Europe. That study was developed in Europe, and something that had to be done to use it was to use superconductors, because superconductors have the additional property that when a superconductive current crosses it, very, very intense magnetic fields are produced. So they used those magnetic fields to drive particles around the facility, but they were not thinking about the high hadron collider when the superconductors were developed. But what they have done also is to design superconductive computers. IBM developed one in the 70s. This is not new technology, but the fact is that the other technologies have become cheaper. And so continuing to work with this sort of technology was not economically interesting. However, another property that I did not mention about the cryogenic computing systems is that these are much faster than traditional computers, between 10 and 100 times faster. And it turns out that somebody realized that when biological things are operating, the living organisms are very complex computing systems. So some researchers started to elaborate on this, and they developed capacities to solve mathematical calculations using DNA. And just to give you an idea of new technologies, there are elements that are taking advantage of the features of quantum mechanics. So instead of working with two value pieces, bits, now we're working with qubits. I will not go deeper into this, but this is now breaking the ground for new technologies that could go beyond the limitations of current systems. Do not forget that the transistors that are Apple computers and Pentium computers and so on were started to be used well, around the 40s. It is a technology that is already mature, that is very well known. Great volumes of information well, these physical components have been compacted a great deal. The last Intel processors have more than 70 million transistors. There are 5 transistors per every inhabitant of the Mexican Republic, for example, can fit on a chip the size of a fingernail. However, that is no longer enough in some cases. Something that I would like to call your attention to is that no matter what technology we use, what will happen is that at some point these technologies will be overcome by the by the volume of information that is being produced. So it is necessary to find something new because regardless of what we do, the volume of information will continue to grow. So I haven't heard this, and probably I wasn't present in the sessions where this was discussed, but it is not the same to speak about data as speaking about information. This is a very simplistic analogy, and I put some origins here to say that information is the juice we obtain from data, and the data are the oranges, and the oranges are not the same size as the glasses of juice. A large orange does not necessarily mean that there's a lot of juice in it. Not necessarily, and the same happens with data. It is not necessary to have, well, having very large volumes of data does not mean that there is a lot of information there. So we have to be very much aware of that because one of the main problems I have seen in practice, now coming down a bit from theoretical uh, concepts, is that at times there is a lot of data, but there is not so much information, and it is something that is at times a miss in designs. And we can try to improve the functioning of our systems by squeezing the oranges better. This is the equation I am sure you were expecting. Now you can applaud if you want. That is the equation. Well, yesterday, some of our distinguished speakers were saying that at times it is not, we do not know if removing a bit will remove information from us. If we are at a village where there is only one school and we talk to the school principal, but if there is information, then it depends on how the information is defined. Information will not be lost just because we removed a bit of information from the text, because that is measured absolutely. And the term entropy alludes to how much average information we have in a data set. Forget definitions, that is not very important here. What is interesting is that we are able to define in an accurate manner and also to accurately measure the information contained in a data set. It doesn't matter what type of data that is. It does not matter if the data is a text written by Miguel de Cervantes. It does not matter if it is a symphony by Beethoven or a popular folk song. We can measure the information there and compare it. We could, for example, analyze a folk song and compare it with the last speech of whomever, and know which one has more information. We can do that, and that does not leave any doubt. We can measure it, we can quantify it, and we can preserve it. This is a very simple example, but what I did is to take that orange and expressed it in this way. Imagine images that have the extension BMP have a lot of images and little information. However, if you take a JPEG image, it has a lot of information and little data, and that is a good example because the relationship between the amount of data in the image at the top and the one at the bottom is a ratio of 17 to 1. If you can tell me that you can distinguish the difference between the image on the top and the one on the bottom, I will not believe you, because these are very similar. However, one requires 17 times more data than the other. However, it is the same amount of information. Something that we can do to better treat large databases is to be more efficient. And thus what we wanted to do is to try to preserve the information without keeping all the data. That is part of the idea, and that is what I will be discussing. Instead of working with a truckload of data, we want to work with information, equivalent information with a smaller data set. We want to extract the minimum sample without losing information and then work with that sample instead of working with that universe that might be enormous. So then, I won't read this, but the idea is that we have to do two things, to guarantee, but because what we want, of course, is that when we are treating this reduced sample, the results have to be indistinguishable to the results obtained after working with that universe of information. Evidently, if you have a set of 100,000 people, you no longer are working with the names of these 100,000 individuals. But if we are going to analyze their behavior, then probably by looking at 100 of them, we can find patterns. And the issue here is that we're finding patterns, and we want the patterns that underlie the original information also stay there in the reduced information. We want to do two things: preserve information, and from the standpoint of details, the information that is in the databases are usually large charts or can be seen as large charts of variables. What we want is to make these variables behave, that the relationships between these variables are the same, whether we consider the entire universe or just a fragment of it. This is what we are trying to achieve. So the first thing is that we want to find a reduced sample that has the same amount of information. And second, we want to model variables. And modeling means here finding... this is a chat without equations, so I cannot add equations here. Probably there's another one. But what we want is to maintain relationships between all the concepts or all the components of the database. I am adding this algorithm so you know that this is actually being done. This is an algorithm that if you were to follow it, you would get the sample with an equivalent entropy to the other. I am just leaving this for you to know that this algorithm exists. You can take pictures if you want. Another one is if I model variables and the object I thought about, and I lied because there's another equation here, but what I want to show with this example is that two very different mathematical expressions give two very similar results. Imagine that the ratio on the top is that of the universe and the one on the bottom is that of the sample. What I want to find are equivalences. It does not matter what is the mathematical formula that models the variables. I want these to behave in the same manner. So I have to ask for two things: that information is not lost and that the relationships amongst all variables remain at such a level of certainty that I can guarantee that if I look at this small sample, I will not realize that I'm working with a very small sample instead of the larger universe. The larger universe, that is my goal. And well, as always, this is some publications have been made on this in this regard, but just wanted to say that this is not an idea that lacks formality. There is a certain level of formality, but I just wanted to unburden you of that load of formality. These are references where all of this has been published, and there is a bunch of equations there for all of those that love them. But well, the point here is that this has been used, and let me give you a case of study. And this is the side of the presentation that has to do with data mining. The study case was when a very large company has very large databases. I'm just gonna say the company to make it anonymous, and it had a very large data set, and we needed to tell them what had to be the size of that sample, what features that sample should have, so that they could work with it instead of working with their larger universe. So the model on the top is the model obtained from the sample. Model below came from the original data. As you can see, is that what we find in these pie charts are the clusters in which we found the subdivision of the customers of this company.
So we found these clusters and we gave them different labels, A, B, C, D, E, F. And if you compare the sample A of the cluster A and the one with the of the universe, we have a 3.1332% difference. So if you analyze the sample and you analyze these clusters, you will realize that they are pretty much identical except for a 3% margin of error in the worst case. The other thing we did was, in case they gave us a sample and we took from the clusters the customers who are in them, what would be the difference between retrieving them from the original cluster or the sample? It's exactly the same. It doesn't matter. It's the same if we work with the sample than with the original universe. So the result was quite interesting. In this company, to create the data for executives to make decisions, it would take them normally 35 days. Now it takes 10 days because they don't have to create the entire system. They add a representative sample. So now strategic decisions can be made quite quickly. And now it's all in the executives' laptops. They used to have to enter the networks. Now they don't. And the methodology was tested for 6 months. And since it worked, this was adopted internationally in this company. So what is done now is that all companies do something similar. So our conclusion: big data cannot be pushed back. It's a snowball. There will be more and more information. Avant-garde technologies will be changed because data volume will continue to grow. And an interesting alternative is to identify valuable information. Let's make sure that our subsamples are equivalent, and that way we can make interesting decisions without being tied to huge volumes of information. But doesn't mean we don't want data repositories anymore. But when we take strategic decisions, we need to know. We don't need to know what the name of individuals are, but what they are doing. So when we identify valuable information, we can make our processes more efficient. Punctual data is not there, but that isn't necessarily used for strategic decision making, and you associate and you lose, or you no longer have the problem of privacy because there's no longer individuals behind this information, because we don't even know who the people are. We know they are sub area of this, and this way we keep privacy and we reduce what yesterday we called the Big Brother effect. Thank you very much.